Welcome to lecture 3 of CS224D. Today we will talk a lot more about word vectors. I understand that last time we went over things fairly quickly. Today we're going to go over all the gory details, lots of analysis, and a little bit more understanding. So let's refresh where we ended off last week. We basically had our main cost function j for theta, which had all the different word vectors in it, and we'll go over all these details a lot more today. I think there's one typo also. So u are the outside vectors, u of o is the index of that word vector, and v are the inside vectors. And let's go over this model in detail again. What do we do at each window? Could you roll up the projector, please? So at each window, let's say we have a corpus here, and let's say today I am giving a lecture. Not a very creative sentence, but true. And so let's say for now we don't have a start word, so we will just start at this word right here, I. And let's say our window size m is just 1, so we just look one word to the left, one word to the right. Now, if we start here, then this will be the vector v for the word I, and then we have the vector u for the outside word for today, and the vector u for am. And now we will try to predict from v which word index we have here on the left and on the right. Right, so just this pair is the first pair that we looked at in our exponent. So here we had the exponent of VC transpose UO. Of course, UO transpose VC is the same thing. And now, in the first step of this window, we're going to look at basically this word pair. So in this case here, for the first window, and our context, our window size of only 1, we will basically have in the exponent here v I transpose u today. And then in the second, so this will be the first element for that window, and the second element we would have the exponent of vi transpose um. Does that make sense? And then, okay, could you raise your hand if this makes sense? For those who haven't raised their hands, do you have any questions? So each of these is going to be one, we'll often call them d-dimensional vector, right? So this is just VC, and UO will always be in RD. And you'll go over that in a lot of details in the problem set 1. And given that there might not be as many questions for your projects yet, I'll have 2 hours of office hour today after lecture. So if you have any questions about this model, it's still a good time to ask. All right, so then in the class we derived, and of course this is just the numerator we had here, the sum over all these words in both cases. All right, we'll use the whiteboard again, please. Sorry, the projector. So on the whiteboard last time we derived the gradient for VC. And I encourage all of you to derive the gradient for the outside vectors u also by yourself, and make sure you can follow that. Okay, so generally when we write that in each window, we'll compute the updates for all the parameters that are being used in that window. It'll mostly be all the outside vectors and the one inside vector. And then you move one over. Now, what used to be an outside vector will be an inside vector, and some of the outside vectors, depending on your window size, might still be shared in each window. All right, so if we had, for instance, a simple sentence here, and we looked at like, and we had our external vectors UI and learning, and we move over one, now learning will be the inside vector, so we'll compute v learning and u like, right? So they switch. Any questions about so generally looking at one window? Yeah?
Do we consider the period as its own token?
Good question. We usually do, yes. In fact, tokenization is sometimes considered a problem in and of itself. In English, we often have quite short words, so it's not that relevant. What we'll notice if we look at other languages, such as German, where you can have single nouns that could have as many characters as some short English sentences, then you might want to split words into their morphemes, for instance, and learn those morphemes. We'll eventually have trouble also when we have numbers, where we have the period or the dot inside, and then there are lots of different numbers. And the question is, do we want to compute a different vector for each different number, or do we want to tokenize that differently and say all digits just get replaced by some digit token like D? So lots of subtlety that we're glancing over, but you'll get exposed to that in your problem set. Great. All right. So now as we compute the derivatives for all the different parameters, we basically would always look at our theta when we start. So theta will essentially have all the different word vectors, and again we have 2 for each word, with the inside vectors and the outside vectors. So this will be a very high dimensional vector theta. 2d times v, d again usually between 25 to 500 or so. V on the other hand could be hundreds of thousands, right? So this is a very high dimensional vector theta. So the simplest thing we could do now to really optimize this is to directly optimize or minimize, in many cases, our objective function j over the full batch, as in the entire training data. But that would indeed require us to compute the gradients for all the different windows. So not only do we have millions of potential words, but we also have many, many millions of windows as we convolve or go over each separate window one at a time, over, for instance, all of Wikipedia, right? And so if we wanted to compute the next update for theta, so theta new during our gradient descent method, this would be our standard equation for gradient descent. And usually we'll use matrix notation for all our parameters, and basically these are all interchangeable. And I want to expose you sometimes to different notation, because on the one hand, it'll be nicer if we use the exact same notation throughout the entire class, but then you might get confused reading the papers that are in the reading materials, and in the papers you'll be exposed to all kinds of different notations. So I want to make sure you understand, kind of see beyond the syntax and see that just the semantics are the same here. All right, so vanilla gradient descent is essentially very simple, both in math and in code. We could just say, while true, we continuously update this whole function. So we have our corpus here, and inside evaluating our gradient, we'll essentially give it our current function j, the entire corpus, and our current set of vectors, or word vectors, theta. And then we just update that. And if this was a simple function, then our updates would just look like this. Of course, in deep learning, we'll never have such a nice, beautiful convex function. So here you see the level sets, and you would see an update that gradient descent does at each time step, trying to get to a minimum. Now, again, our corpus may have 40 billion tokens, and hence over 40 billion windows. And if we had to evaluate all of them to make a single update, we would wait a very long time before the model does anything. And we wouldn't know how well it does until we actually make the update. And it turns out that this is, in almost all cases, a very bad idea for neural networks. In none of our assignments and in none of our implementations will we ever use full batch gradient descent, where we go over the entire training set and then make one update step. What we'll almost always do is to update our parameters after we see each window. And then we'll immediately see whether we're improving things. We can immediately evaluate and visualize what's going on. And in almost all cases, instead of summing over all the windows at time steps t, we'll just basically make one small update at each window. So also very simple code. Instead of just looking over the entire corpus, we will sample a window. The simplest thing is to just go one word at a time to the right. And then we will evaluate the gradient only with respect to the word vectors that are in that window, and then make an update step. Are there any questions about stochastic gradient descent? Yeah?
Maybe I missed that part. How do you initialize the center and the outer vectors?
That's a great question. So how do we initialize the center or the word vectors in general? Basically, they'll all be very small random numbers. So usually we'll initialize all the u vectors in something like a uniform distribution between minus 0.001 and 0.001.
So for the same word, the center and the outer vectors are eventually going to be different.
That's correct. Yes, the u's and v vectors will be different. They will capture slightly differently the statistics of co-occurrences. Yeah.
Do we know if the likelihood function we're optimizing over is convex?
We know that it's not.
Oh, okay.
And that will be an unfortunate truth for almost all the models we will look at. None of them will be convex, and all the beautiful convex optimization will usually go out the window. Hence, there are lots of interesting optimization questions in deep learning, tackling saddle points, and so on. A few of them we will actually go into in this class, but if you are so inclined, you can evaluate those for your class projects, but it's hard to make a really impactful class project based on the optimization. You have to be pretty good at optimization. A lot of the ideas from convex still kind of hold. You will try to approximate things, for instance, with stochastic gradient descent. Sometimes you can look at second order derivatives to try to get to your local optimum more quickly and so on. Of course, the entire shape of our objective function also changes with each window, and it changes to different non-convex sort of manifold you're trying to go over. Any more questions? Yeah?
I'm assuming there's a problem with just initializing to 0?
That's right. You do want to initialize to small random numbers. If everything is 0, then in the beginning, you're not going to go anywhere. In some cases, it'll be hard to.
So will the gradient become 0 or something?
Let's go over that. So here, what would the gradient be if this was 0? What would the exponent be?
1.
That's right. So it won't be 1, but it will be in a very bad, usually when you optimize, it'll start in a very bad place. And also there will be symmetry issues and so on, so you do want to use small random numbers. All right, great. So really our update at each window t, let's say we have this simple first window of I like deep learning or I like learning. We will only really have 3 of the vectors actually be populated in this very high dimensional update vector, the gradient with respect to theta. Right? We'll have only derivatives for the inside vector of like and the 2 outside vectors of I and learning. And so instead of actually creating that, and this will be very important for all your implementations, because if you implement everything naively with single for loops and indices and then gigantic vectors where you're going to go over every single one and you have here a million numbers that are all 0, it's not going to be very efficient code. And so there are a lot of things that we can do that are much smarter than that. Essentially, we're going to want to only update the word vectors that we actually see at each window and not keep around all the zeros for all the word vectors. And so we can keep around basically a hash, a mapping for all the word vectors, and only update certain columns of this full embedding. So one is either you have a large hash that has, for each ID, you get the word vector, and then you look at the ID of that word vector and you get the word vector. Or you have one very large matrix that you can efficiently index, and then you just basically take out specific columns of that matrix, and you update only those columns. Yes?
So are you saying that we're storing theta in this kind of different form?
That's right. So you can essentially decide how you want to store your theta. It could either be the word matrix. Usually, sometimes we call this L for the embedding matrix. In our case here, we'll call it capital U, which has all the U vectors, and then capital V for all the V vectors.
So there's going to be 2 of these.
That's correct.
One's D by V, and one's D by cardinality of U.
Yes. So here, when I write this notation, I usually just mean the size of the vocabulary. So that will be the same for both U and V, because all the words will appear in both.
Which method do you recommend?
I usually have a big matrix that I efficiently can index. But I encourage you to play around with both, and you can even mention those. All right, now in problem set 1, as I alluded to in the last lecture, you will realize that this normalization factor here is much too computationally extensive to actually compute for every word pair of inside and outside vectors. And so instead, we will actually implement the skipgram model, which is the most popular model in sort of the word-to-vec family. And the main idea will be that instead of having one softmax where we try to penalize and basically lower all the probabilities for all the words that don't happen to appear, we'll actually only look at the true pair of a center word and its context word, and then we'll look at a couple of random other words, a small set, maybe 10 or 20, and we just push those down. We don't push down all the words that don't happen to appear in this current window. And intuitively, again, what we're basically doing here is if you try to learn the vector for zebra, it doesn't help you that much to tell the model that zebra doesn't co-occur with these million other words. It's mostly helpful to say it does co-occur with, I don't know, Serengeti or lion, and then it doesn't co-occur with a couple of other random words. It's not that helpful to say it doesn't co-occur with all these other words. So let's go over the objective function that you will implement, and this is from the paper Distributed Representations of Words and Phrases and Their Compositionality by Tomasz Mikolov. And the main objective function will again be our capital J over theta, now being all the word vectors. And we'll again look over each single window, and I'll just basically write this here. T is basically it goes through all the tokens, all the potential windows that we have, and JT of theta will be the objective function at that window. And because we do stochastic gradient descent, we'll basically only ever evaluate one JT at that window. And then what we'll do is we'll actually maximize here this inner product, and if you're familiar with logistic regression, you'll see logistic regression again here. It's basically just a binary problem, and we want to maximize here the probability of these two words co-occurring. And then we will go over a couple of k random word IDs. So I equals 1 to k, and for each I will basically randomly sample a word index from our whole vocabulary. So out of the millions of words that we may have, we may only sample 20. And then we will try to minimize the probability of them co-occurring. And if you don't find it intuitive that we're minimizing this, one thing you might want to look at and prove to yourself is that the sigmoid of 1 minus x is the same as 1 minus the sigmoid of x. I wish I could just write something on the board. So sigmoid of minus x equals 1 minus sigmoid of x for the people on the left side of the. Yeah. Yes?
Is there a rule of thumb for a number of negative samples to use?
There is, and I will show you in a couple of slides at what point it becomes not as useful anymore to go above. But usually 20 or so is a good number.
Do we fix the random like negative samples on every iteration or throughout the whole batch of the update?
Do we, sorry, say that again?
Do we fix the number of, I mean the specific words that are not co-occurring on every iteration of SGD or for the whole like epoch, for the whole batch?
We'll usually have a completely random sample for each window.
Is PFW a uniform or?
I'll actually show you in the next slide. All right, so just a refresher here, the sigmoid function is a very popular function. We'll use it a lot, and you're going to want to really understand all the derivatives you could possibly take with respect to anything inside a sigmoid or using the chain rule with sigmoids. It'll be very important for the midterm and all the problem sets. Basically, it'll just take any random number and map it to be between 0 and 1. And then in deep learning, we'll just say, well, if it's between 0 and 1, we'll call it a probability. It's not a really great way to deal with probabilities, and if you actually took the graphical models class like 228, you kind of cringe a little bit, but that's how we often roll. All right, so we'll use the sigmoid function a lot. It is not the most popular function in internal layers of deep learning, but it is very popular, especially if you have just a very simple binary problem at the end. All right, any questions about that objective function? All right, we released the problem set this morning, so I encourage you all to get started hacking on it. So here it's just a slightly cleaner notation. Instead of summing over this index and you sum over k and then you sample j, sometimes we just write we sample a couple of j indices from our word distribution, and somebody already asked, is it a uniform distribution? One thing that actually often makes sense is to sample more frequent words also more frequently in this, and so the answer is that empirically something that worked was to take basically this function where you have here the unigram distribution, so just how often does each word appear in general in their corpus, raised to 3/4 power. And we'll provide this function in the starter code, so don't worry. Basically, yeah, the power here makes less frequent words be sampled slightly more often, but not as often as if it was completely uniform. Yes?
Isn't the point that we want to sample words that are often co-occurring?
That's correct. So we still, if it was completely uniform, we would sample very rare words like aardvark as often as very frequent words like hello. And so here we will sample those more frequently, but not crazily so. Basically, if we, because you usually have a very much a power law kind of distribution, so the most frequent words appear so much more than very rare words, we want to basically attenuate that a little bit. still encourage slightly more frequent sampling of frequent words, but not as frequently as they actually appear in a corpus. All right, great. So mostly we focused on the skipgram model, where we take the inside vector and we try to predict the outsides. The main idea for another very popular model, the continuous bag of words model, is actually quite similar, and you'll look at both in problem set 1. But we can, instead of predicting the center from the center word, the outside words, we can also average all the surrounding words and try to predict the center word. Very similar idea, but slightly different, results in slightly different results. And in the end, again, somewhat hackily, we might also combine the two and average both. Turns out to also work well. But basically, the idea is very simple. Instead of taking the center word, trying to predict the surrounding words, you can take the surrounding words and try to predict the center word. You won't actually have to implement the continuous bag of words, because I think once you implement the skipgram model, you'll kind of get the idea. I think it'll be a bonus point question. And if you implement your code well, then it'll be very easy to just switch that in and get those bonus points. All right, so that was the main model of Word2Vec, the skipgram model. Are there any more questions around that?
How do you pick the dimension unit?
How do we pick that? I'll actually go over that a little bit. We'll get to that in a second. It's a great question, and it's very important, hence we have lots of slides for it. So then at the very end, we mentioned a couple of advantages and disadvantages of these different models that we looked at in the beginning, models that are based on SVD or PCA versus the one window at a time approach of the skipgram model. And we ended on this equation where we didn't have much time to go over it. So here, the idea is, instead of going over one window at a time, maybe what we should do is we collect the whole corpus and we basically collect all the co-occurrence statistics. So for each row, so what we started out with, right, when we just used the SVD approach. But instead of now running all of SVD, we're going to sample and actually go over each of the indices of that gigantic matrix X. And we're just going to optimize this function for all the word pairs, ij, in the corpus. So here, we basically will also want to minimize this squared loss, where log p is basically just the log of the probability, or of the counts in many cases, of how often words I and j co-occur, and want to be able to make their inner product predict how often they would co-occur. And that is essentially capturing the similar idea of Word2Vec, but instead of doing it one window at a time, you once collect all your co-occurrence statistics, and then you can run the optimization over that. And that Pij matrix, or we often call it X also in the first lecture, or the second, is also going to be very sparse. So we're not going to have to go over all possible pairs. And then because we have some of our word pairs, like the and cat, for instance, or he and has, those word pairs appear so often, they would have a very, very large impact on this objective function. And so what we found empirically is to actually just cut off in this f function here and have a maximum that I think is usually, yeah, we basically don't want to force the very large counts to dominate the entire objective function. And so we'll cut that off and have a linear scaling until then. Does that make sense? Basically, otherwise the model would spend a lot of its parameters making sure to capture the and cat and he and has appear very, very often together. And it will kind of dominate the rest of the model and the rest of the optimization. Yes?
I'm sorry, what was the Pij again? Like what's
So these are basically the co-occurrence counts that we started out with when we looked at the SVD-based method. And you can, in various ways, pre-process those co-occurrence counts. You can look at correlations instead of just the raw counts. There are lots of tricks, but the main idea is you just take some transformation of those co-occurrence counts. Cool. Cool. So this will be scalable to gigantic corpora, right? Because we only once have to compute the counts, and then we can store that matrix and then do all our math afterwards on that matrix, which is a lot smaller than the original corpus too. And because this makes very efficient use of the statistics, it'll also work quite well on smaller corpora. So let's look at a couple of the results. This model is the GLOVE model, global vector model. And if we now look at simple inner product similarities and distances, we can basically find that, for instance, for frog, the next nearest neighbors in our now usually 100-dimensional or so vector space are all different kinds of frogs. So even for very rare words, this model does phenomenally well, because these crazy words here are also just different kinds of frogs, but they're just not as frequently in the corpus as simple things like toad and frogs. So it captures similarities very well between both very frequent and infrequent words. Now in this model too, what you notice is you have here u and v vectors, which again is not very intuitive, because here I just showed you similarities of just a single word. And so the question is, which of those words do you actually use, or which of these vectors? And it turns out after we train the word vectors, in almost all cases what we'll do is we'll simply sum them up or average them, or in some cases concatenate them too. And that is, depending on how you evaluate, and we'll get to that in the next slide, another hyperparameter that you can compare. Should you actually concatenate the two or just sum them up? The most common thing is to sum them up. I think we had a question.
Yeah, I just wondered why it's much more efficient to train this model, because it doesn't seem like a priori you still have to train to optimize each of these vectors. You still have to compute the gradient for each of these vectors, isn't it?
Yes, but you basically only have to compute the gradient for each of the co-occurrences once. So imagine the word, I and like appear in the same corpus 50,000 times. Like in actually 50,000 separate windows, you now want to say these two things co-occur, improve the probability of those co-occurring. In this model, you have to do that only once, because you already collected all the counts, and you're just going to say minimize basically the distance between the inner product and some transformation of those co-occurrence counts, right? So it's a lot more efficient in that respect. You immediately go after the statistics instead of going after each sample once and hoping that eventually the statistics will fall out of the model. It's a great question. Yeah.
So it looks like in like the straight word to back, like the co-occurrence matrix never really makes an appearance.
That's correct.
It's completely incidental that they might be related, whereas GLOVE is precisely trying to optimize against the co-occurrence matrix.
That's correct.
More like happenstance and sort of.
Yeah.
It's just purely an alternative to SVD as a way to approximate.
That's right. That's right. Cool. All right. So now, how should we evaluate these word vectors? Before we go there, are there any last questions about the word vectors? Okay. Well, if there are still some, I'm sure you'll get to them very soon, because the problem set will force you to. All right. So basically, in general, in natural language processing, and in most applied machine learning fields, you will have, in many cases for your projects, two options for evaluating how well you're doing. And in some level, the two options are extrinsic and intrinsic. Intrinsic, usually you evaluate on some specific or intermediate subtask. So for instance, how often do words appear in specific relationships, like king minus man plus woman goes to queen? Or dollar minus America plus Mexico goes to pesos or something. So you can basically evaluate that, but in the end, you don't usually care about your intrinsic tasks. but they do help you to basically very quickly evaluate how well you do. In many cases, word vectors are really step one to a more complex natural language processing model that actually does something useful, like machine translation or sentiment analysis or question answering or things like that. But every time you tune your model and your word vectors, you don't want to have to then plug those into some other model that also takes potentially days to train before you get some response of knowing how good your word vectors were or not. And so usually it just helps you to just understand that specific model, in our case the word vector model, and iterate very quickly on that subproblem. However, whenever you do this, you do from time to time want to make sure that there is actually some correlation between your intrinsic task, and we'll look at the word vector similarity and analogy task, and make sure that actually improvements on that intrinsic task have at least some correlation, some positive correlation with the accuracy of the task you eventually care about. And because there are some people who literally spend their entire careers optimizing these intermediate metrics, literally years of their lives in their PhD, evaluate these intrinsic metrics, and then some other PhD a couple years later finds that there's actually not a great correlation between that intrinsic metric and some other metrics that most other people would care about. And that would be quite the pity. So that leads us to extrinsic tasks. Basically, it's a real task, like I said, semantic question answering, sentiment analysis, things like that. In general, it's preferable. However, in most cases, especially in deep learning, it will take a very long time to actually compute an accuracy for a very complex model, especially, for instance, machine translation. It can take weeks to train a machine translation model to high accuracies. And once you evaluate on the whole model, it's also sometimes unclear if you improve that whole model because your subsystem improved or because you improved other pieces of the system. So whenever you want to write a real academic paper and you say, well, I have better word vectors, and I'm going to show them on some other model, you want to very carefully tease apart all the potential changes that you made and then be able to drill down and say it's because of my novelty in my word vectors that the overall sentiment analysis model actually improved. And so in general, you want to have both. That's the best you can do. But you'll observe it'll be hard to have both in most cases. So yeah, this is an important statement if you want to write papers that actually get accepted in real academic conferences. So replacing one subsystem with another improves your accuracy, and everything else is fixed. Everything else is the same. Then you know that your subsystem actually made a real improvement. So let's look at both intrinsic and extrinsic evaluations for word vectors now. Intrinsic word vector evaluation, one of the most popular one that sparked a lot of interest are these word vector analogies. Basically, if we say that man is to woman as is king to something else, then we would ideally hope that somehow in the geometry of our space, this is captured. So if we take, for instance here, the vector difference of man minus woman, and we get this vector here, and we did the same thing for king, then ideally up here, our word vectors would have placed queen. And so we can essentially just use here this cosine distance after all these additions, and we find the argmax, the vector that maximizes essentially this cosine distance. It's normalized inner product. And we should note here that in all these evaluations, the other input words, as in man, woman, and king, are usually discarded, because otherwise they would often come up as the best answer. And I want you to think critically about this. This is one way. It's very popular. Hundreds of papers have come out about these kinds of analogies since, but we can still be skeptical, largely because your word vectors may include all these analogies, but it might not be in a simple linear kind of way, right? Maybe it's a more complex nonlinear function that has to be learned to capture these. The amazing thing here, though, is that there's no extra function needed that needs to be trained. It just happens to fall out of the co-occurrence statistics that we're able to capture with GloVe or Word2Vec kinds of models. And when we run PCA on a bunch of different pairs of words, here are some of the examples that fall out. And we basically see that the vector differences look very similar, and that will allow us to then also say, well, basically, if whenever you take this one minus that one plus this one, it will go to whatever is at the end of that vector difference. So brother is to sister as nephew is to niece. Or sir is to madam as heir is to heiress. And for some, they're even nicer and they go exactly in the same direction and have similar lengths, and in others they're not quite, but still go roughly in a similar direction and have roughly similar lengths. Of course, the length shouldn't matter because we'll use the cosine distance here. But for this, this visualization, you still see that there's a difference, which we'll get rid of in our evaluation. It even works for some more modern things, such as companies and their CEOs. And again, you might think this is kind of magical, but really it's just straight up co-occurrence statistics that are being captured, right? All these people usually appear in similar kinds of contexts to their companies, like is leading or made an announcement about, and so on. So you would assume that whenever you try to take these very large vectors or co-occurrence statistics and you collect the right kinds of statistics with the right window sizes and so on, that you eventually capture these kinds of similarities. It's still pretty cool, don't get me wrong. We're all, like the whole field was very excited to see that these relationships, when you project them down, look that linear and are that consistent. It also works for other sort of more grammatical things like superlatives. Here you have slow, slower, and slowest, for instance, or short, shorter, and shortest. They're all also in very similar kinds of geometric relationships. And this, of course, is great because once you have an unsupervised system like that, it may allow you to say, well, I don't need to know that much about the domain, but just from looking at these linear relationships, I may be able to look up facts, quite logical or discrete facts, despite everything being just in these fuzzy co-occurrence statistics. All right, so let's look at a couple of examples and think critically also about what they're being captured, what is actually being captured. So here we look at the word vector analogies. Now they don't actually have the CEO in this actual data set, because in the end, if you're optimizing something, you want to see is your new model idea actually improving the state of the art. You want to have some real number, not just a bunch of cute examples. And so to get the real numbers, these are some of the subsets of actual triplets where you usually take out one of the words and you see if you can recover it. So Chicago minus Illinois plus Texas or something should go to Houston. And so here we have city is in state relationships. And of course the problem is that different cities may have the same name, right? And one city might be, so there's for instance, there's a Paris and a London somewhere in the United States, right? So what we'll notice eventually in many cases here is that the city name that is the most frequently used is the one that you would get right. But of course, there's some problem with this. Does this make sense of how we compute basically? You basically do this evaluation, this argmax, and you try to find if the argmax D here is actually the right last word in these two relationships. So city and state is one. The capital is another one. Of course, here the problem is that those might change also over time. Then we have a lot of superlatives. So bad to worst should be bad minus worst should be similar in vector direction as big minus biggest, for instance. With past tense, dancing to danced should be similar to decreasing and decreased. And of course, there are lots of examples that we can collect. So in the end, we'll have tens of thousands of these kinds of analogy pairs, and we can really see if our model captures all of them consistently. Yes?
Would these analogies still hold up if the training data had been stemmed prior to training the model?
No. So stemming refers to basically taking away, for instance, the ing or the ed, and you just say decreasing and decreased all get changed to just decrease without the e at the end, and then you would lose all of those.
But conceivably, you still have similar context around something like dance versus something like throw. So you would still have that relationship of
I mean, you'd have some, right? I'm not saying they would all be gone. You would still get the cities because those usually don't get stemmed very much. But for instance, the past tense you would lose if you stem. Yeah.
I had a question. Would you retrain your model for different corpora, or for the English language, would you have just a set of vectors?
It's a great question. So would we retrain for different corpora? In many cases, it's just best to train on the largest possible corpus you can find. So if you have multiple corpora, you just put them all together and you train on the final biggest possible thing. So let's look at what that actually means. So here's a very careful analysis of the skipgram model, the continuous bag of words model, which we now know very well. We haven't really looked at these two, so let's ignore those for now. They're also rarely ever the top vectors. And we have the glove model here that we've also looked at in more details. And then we have actually the very simple SVD baseline, and then there's several ways, which we won't go into details of either, of tuning SVD to actually improve it a lot too. But sort of the straight up SVD baseline that we looked at in the very beginning is mentioned here as well. And so now here we basically try to disentangle what matters more, the dimensionality, for instance, of the word vectors versus the size of the training corpus. And so, for instance, if you take the glove vectors, they're 300 dimensional, and you train it on 6 billion tokens, then you would get an accuracy of 71 in terms of these word analogies. So we had tens of thousands of examples such as these pairs, and we basically look is the ID with the argmax of the cosine distance that we defined a couple of slides before, actually the ID of flu, for instance. And then we look at how often is that actually the case, and here it's 71 and 71% of the time, the cases, it is actually the case. But if we train on 6 billion, on 42 billion, it improves significantly by over 3%. So just the same model, same vector dimensionality, but a larger corpus, in almost all cases, basically gets us the best performance. And it didn't even make that much sense here. We basically also can compare, and this is very important again, and something that it has to really get into your mindset to do well in your final project. You want to only ever change one thing at a time in order to really understand these machine learning models very well. So here we also looked at having the exact same corpus, same size, at 1.6 billion, but changing only the vector dimensionality from 100 to 300. And we again see here that 300 is much more accurate, over exactly 10% in total, than just having 100. So basically projecting down our very high dimensional core occurrence matrix to just 100 dimensions just loses too much information. But at 300, we start to see really good performance. And then we can again here compare and go even further and have 1,000 dimensions, for instance, but 1,000 dimensions then actually keeps around maybe too much noise and actually works slightly worse, having the same corpus size, for instance, for the skipgram model. So skipgram here and skipgram here, 1,000 dimensions, 300 dimensions actually decreases. And so really what we want to see, and what I encourage you all to do in every machine learning project ever, but especially in your class projects, is to compute and visualize the performance in as many plots that are sensible as you can. So let's look at the word vector dimension, for instance. Here we basically see, and we can mostly care about the overall, that basically combines semantic things like gender or cities and their states and their capitals and things like that, and syntactic things such as bigger and biggest, superlatives, or different tense of verbs. We combine these in the overall. And we basically see that in terms of word vector dimensions, as we have higher and higher dimensions, at some point it levels off and it doesn't really improve. So between 300 to 600, there's almost no gain anymore. And hence, it doesn't make sense to go much beyond 600. Also, of course, the lower dimensional, the word vectors, the more efficient your whole system is, right? It's much faster to train, smaller inner products, it's much more efficient. So in terms of efficiency, you want to ideally find the smallest vector dimensions that still give you the highest performance. Then window size was also a common question. How many words to the left and to the right should we actually predict? And here we also see actually something that's quite interesting and actually very intuitive. Syntactic performance actually decreases if you have windows that are too large. Because at some point, if you just look at 20 or 30 words to the left and 30 words to the right, all of which have no order, right? We just essentially had said that we just try to predict center word times u, the outside word. We don't care how far away the outside word is. It could be 1, 2, 3, or 4 to the left or to the right. And so if you make this larger and larger, at some point you will lose syntactic structure. Syntax captures grammar, grammatical structure, and if you have very large bag of words or no word order kinds of models, it will hurt the grammatical understanding that the model could capture. But semantics actually keeps going up. It turns out if you talk about a king, a lot of the words around that word are still roughly in the same kind of semantic space. So if we care about the overall, we basically see that around window size of 8, and again here, the smaller the window size, the faster and more efficient your model is too. So in terms of efficiency, you would like to keep the window size very small. And then here we actually look at the asymmetric context. So we look at only the words to the left, for instance, and we see that in general it performs reasonably well and has a similar kind of trade-off curve where you don't want to go too far and have a window size that is too large. Yes?
When we smush together all these documents together, and we have this window, can the window span 2 different documents?
Yeah, usually you don't care about that.
Okay.
You just let it go over it. It makes not that big of a difference. All right, so these kinds of plots you will want to produce in all your projects too. And sometimes it's actually hard if you want to compare two different models that are very, very different. It's hard to compare them properly. So this was an attempt at doing this where we say, well, maybe all that matters was training time. So you also want to make sure that if you compare vector dimensions 300 or 100 versus 300, maybe the 300 will eventually be better, and we know they are, but maybe they also take more time. Right? You can't just train both models for 1 hour, because maybe the 300-dimensional vectors will be worse after 1 hour, but then much better after 5. Right? So it's very, you have to be very careful and question all your assumptions and all your hyperparameters. These hyperparameters are, how long does your model train, what's the vector dimension, what's the window size. We call all of these kinds of higher level parameters of your model the hyperparameters. You want to be very careful at analyzing these. And so here, what we tried to do is basically compare both the time, but then as iterations as well. So how often do we go over the entire co-occurrence matrix? It turns out it's much better to go over it multiple times. So kind of countering the question of, you still don't go over each window as often as the words co-occur, but you do go over it 20, 40 times or so over that entire co-occurrence matrix. But it turns out that GloVe, for instance, is still more accurate in terms of these analogies on roughly similar times trained. And one way to account for that for the skipgram model is to actually look at the negative samples. So those were the number k that we had, where we summed over a couple of other random words. And here we basically can see that it makes not that big of a difference, but around 15 or 20 is usually a good number to just push those probabilities down for other words. Any questions about the evaluation? Yes?
About the intrinsic evaluation, and I might be wrong, but can you also evaluate over like phrases, like you normalize a phrase and then you want to see the correlation, like, you know, maybe like Keene is a, or like Paris is a city of light as New York is to not just across words, but if you actually aggregate.
Yeah, so it's a really interesting question. How would you deal with phrases and trying to have analogies for phrases? It's actually much harder to come up with a nice list of 10,000 examples to have an efficient way to evaluate, yeah, Paris is the city of love, and I don't know, New York is the city of lights, you know, it's like, it's a little unclear. And it's actually generally a tough question. What should vectors that capture longer phrases, what should they actually capture? It's much less obvious than it is for words, because some vectors you might want to capture that they're resulting in an action, like answer this email or go get the groceries here or something like that. Other sentences or other sentence vectors might just capture an emotion, like a sentiment, is this positive or negative? There's so many things sentences can capture that there's no obvious way to deal with analogies like that. All right, now, usually I said more data helps, but if you had to choose what kind of data you train these word vectors on, then it actually also helps to use Wikipedia. For instance, if you said I only have this limited computational budget, so I can only run it on one specific corpus of 1 billion tokens, and now you had the choice of a news corpus or Wikipedia, in many cases Wikipedia is better. So looking at, for instance, the overall accuracy here, if you use GigaWord, which is mostly news text from different newspapers, it's actually larger, several x larger than the Wikipedia from 2014, but it still results in an overall worse accuracy on this intrinsic task. Yeah?
Do we know why syntactic tasks are harder to see than semantic?
Why syntactic are harder? We have no nice proof for it, but basically you might not see all these different adjectives, for instance, together or in general as frequently. So we talk a lot more about facts, especially in Wikipedia and the news. We have a lot more sentences about different cities and different currencies and so on in semantics than we have, that we talk about the darkest place or something, or the greatest something. So these generally are not as frequent, and that's an unfortunate truth for a lot of this. It really, the models are only as good as the training data that they have. Yeah.
What happens if you mix like a random mix of multiple training sources into your training model?
I mean, that's essentially what Common Crawl is. So Common Crawl includes Wikipedia, includes all the different newspapers that allow themselves to be crawled in their websites and so on. So Common Crawl is really just 42 billion tokens of internet text. And so it's a very broad range. It includes Wikipedia, and it's usually the best you could use. But it's also a huge pain. I wish you could all do that and use Common Crawl in your projects, but it's unlikely you'll be able to just deal with the gigantic size and the machines that we have. A couple of days at least if you have a very, very efficient C++ implementation. And as soon as you go to Python or something, you'll be talking about weeks. So yeah, you're already too late. Don't do it. All right, now another intrinsic word vector evaluation that is very common and has been used a lot more in the past is actually just look at similarities. So you look at inner products and you say, well, if we asked a bunch of humans on a scale from 1 to 10, how similar do you think tigers and cats are? Tiger and cat, these two words, then they might say, well, if 1 is they have nothing to do with each other, and 10 is they're basically synonymous, they're exactly the same, then tiger and cat is 7.3. Very subjective, of course, might be culturally dependent, and so on. Usually, you just ask a bunch of college students who are around when the researchers did their research. So they're again, potential problems, but in general, it's helpful, right? Because if you think that your vector similarities or inner products capture these kinds of human similarity judgments, then maybe eventually, if a model is trained, and now you see paper and book, for instance, and you're trying to classify, is this something about reading or is this something about watching movies or something? And your vectors captured at book and paper are actually kind of similar. Then maybe a subsequent model that you train on for classification might make use of that and get better performance. So you want basically these word vectors to capture these relationships. And computer and internet, of course, they're very different. Sometimes they're subsets. Sometimes they're just different kinds of words for the same thing. Sometimes they're hypernyms or hypernyms and so on. Just in general, you'll kind of get the idea though here. Here's basically a random sample. So professor and doctor is 6 out of 10 on similarity according to a couple of human judges, but a stock and a CD is only 1.3. And now you can also look at basically just correlations between these different vector distances and the human judgments. And you want to basically have high correlation. And again, the glove model that is trained on a very large corpus does very well on a lot of these different kinds of similarities, and has basically its inner product distances have high correlation to the human judgments. And there are a couple of different corpora that are available. This one here is very popular, though it is very small. It just has 353 word pairs. And in the end, as you dig into this space more and more, you realize there's been so much excitement. People have done so much work on that also since GLav in 2014. Hundreds of more papers came out, and you can now combine the different ideas. So for instance, originally skipgram just looked at the concatenation and maybe just the v vectors and not the u vectors. And then GLav realized, well, if we train v and u, but then in the end we sum them up, we actually get better performance. And then you go back and say, well, maybe if you did that for skipgram, that could improve the skipgram models too on all these evaluation metrics, and you can basically combine all the various ideas of the different models in various ways. All right, so now one question that came up already is what happens if we have ambiguous words. So for instance, you might say run could be like I had a good run, and it's a noun, or it could also be a verb. We all run every day. And then you're basically now, when you're training the model, you pull the vector for run into different directions. If it happens in a noun context, you pull it into the noun direction and you pull it closer as you visualize this. And this is actually kind of cool. I don't think anybody has done a really good job at it, but I've sort of internally, when I played around with word vectors, tried to do this during my project. And kind of as we train the model, you can kind of see how the words start to move around. And so intuitively, when I say it's getting pulled in different directions, you can kind of see as it's optimizing in this 100-dimensional space, you project it down to 2 dimensions, and then you look at what happens after you train for a while, you see that different words get pulled in different directions. And so as you train for each new window, for instance, in the skipgram model, and it's a noun window where run, for instance, the word happens to appear as a noun, it basically gets pulled closer to other nouns, and then gets pulled away again and goes closer to walking or something if it's in a verb context. And so one way we thought about dealing with this is to essentially cluster the word windows that we have. So imagine you have your v vectors and your u vector, and you just concatenate all of these vectors. Let's say you have each vector is d-dimensional. You basically have a window size of 1, so you have 3D dimensional vector, as in 3 times d. And now you basically just cluster all of these with some simple method like k-means. And then you assign IDs to each of the words based on those clusters, and then you can train basically with each word having multiple indices and multiple meanings and multiple vectors. So you will eventually have bank 1, bank 2, bank 3, and so on. And when we visualize those, we actually see that the model can capture some pretty cool kind of ambiguous words. So for instance, this is hard to read, but this is bank 2. And bank 2 is close to banking and finance and transaction, or laundering for money laundering, whereas bank 1 here is close to plateau and boundary and canal, and it's basically the sandbank, whereas this is sort of the money bank. And we have here star, and there's one star that's close to galaxy, and here we have another star that's close to movies. And you basically it learned that there are different kinds of stars, like movie stars and galaxy types of stars. And there are lots of other examples. Jaguar, it's actually I think an instrument, a bass guitar manufacturer, but it could also be a software, and could also be the Jaguar, actually the animal, and that would then be close to hunter. So while that is very nice and has better performance, of course, on certain similarity metrics, where if you actually create similarity metrics where you have to be able to tell the difference and have to be able to say, well, this word has different meanings in different contexts, it works better on intrinsic tasks. But to be honest, for extrinsic tasks, it doesn't often make a difference. The models that you put on top of that, which we'll cover in the next couple of lectures, will do just as well if you do this as a pre-processing step or you don't. So in many cases, if you just have very high dimensional vector, it turns out that some of the dimensions implicitly seem to capture that words can have different meanings. So as cute as this idea was when we published the paper in 2012, I don't think it's very necessary for most of your projects. Now, these were all intrinsic evaluations, and basically what I would encourage you to do is actually is to look at extrinsic word vector evaluations too, if you work with word vectors in general. And one such example would be to do named entity recognition. And in the next lecture, we'll actually cover a model to do named entity recognition and with deep learning. And once we understand that, we'll understand really how we got to these numbers. But basically, this also shows that sometimes the differences aren't actually as big. So remember how SVD was really, really bad for the intrinsic task? Well, it turns out it's only around 3% worse on a real task of named entity recognition, for instance. So we did all this work, but in the end, it doesn't make a huge difference. Though, of course, like 5%, that is very statistically significant, and it's definitely worth a paper, and you're pushing the state of the art, and so on. So these are all great numbers to improve, but the differences might not be as large as the intrinsic evaluation suggested. So all that you need to understand, for instance, for named entity recognition, is that it's a person, organization, or location. It doesn't really matter that this person, like the CEO, is in exactly that relationship with that company. You just need to know it's a person, right? And that might be already captured in much simpler word vectors that you got with simpler methods. All right, now, on the one hand, it might not make a big difference if you use SVD or skipgram kinds of models. On the other hand, training single word vectors actually has several benefits. And using deep learning methods will have even more benefits, because eventually we can train the entire system end to end. We'll have a very complex model, a recurrent or recursive or convolutional neural network, that takes as input these word vectors, but we can actually train the word vectors as part of the overall model. And that's when we'll have very powerful, we'll get, I think, the highest accuracies in almost all cases, if you have a large data set. So generally, the benefit that we get from these methods is that similar words will cluster together, and then that will help us for downstream classification tasks. So for instance, when we want to do named entity recognition, we want to classify locations. Well, if all the location names cluster together, then it makes it much easier for the classifier to find locations, right, and build sort of a decision boundary around all the word vectors that have locations. It's also amazing that we actually showed in many different papers that word vectors can really capture facts, like discrete kinds of facts, and you can later query also these facts from the word vectors. So when we actually want to classify, in the end, we will not just train the word vectors for their own sake, but we'll actually use so-called softmax if we want to have any kind of multi-class classification on top. So this will be a little boring again for those of you familiar with logistic regression and very familiar with it, but it's still good to look over the notation and basically introduce this. So now that we have word vectors, we usually don't end there, right? We want to train some system that predicts some output, some class, based on our inputs. The simplest thing we could do for now is just train word vectors after we train them in an unsupervised way, and then we classify the different word vectors into different categories out of context. It's not a task that we'll actually really have to do very much, but just for illustration, and we can go to more complex things in next week in the next lecture. So let's define the softmax, because that's one of the most basic building blocks for our neural networks. Again here, we'll start, for instance, with a simple word vector x. That is, in many cases, the average of our u and v vectors. And this is the notation that we'll usually use for the probability for a class y given some word vector or eventually some other random vector x. And we have our exponent here, and this notation w y dot will basically mean that we take the yth row of our matrix w. So if we have C classes, we'll have C rows and D columns. And because W, the row, is already a row vector, we're not going to write the transpose here. And then we normalize this over all our classes so that overall our probabilities for all the classes y will sum to 1. All right. We'll essentially interchangeably use logistic regression and softmax classification, yeah, we will use those interchangeably. And we already had the sigmoid. Sigmoid is perfectly fine if you just have two classes, right? Then 1 minus the output of the sigmoid is the probability for the other class. But the softmax will allow us to have lots of different classes. All right. Let's look at some more terminology. As we train our softmax, I'll sometimes use the word loss function or cost function or objective function. It's somewhat interchangeably. Usually when we say cost or loss, we want to minimize it for sure. Whereas objective function, sometimes we minimize it, sometimes we maximize it. And you have to be paying attention to which one we use. Generally, as we compute the probability for a certain class y, like I said, we take the yth row of w. And this is some of the notation that we may use. So if we have this inner product here, it's basically just taking the yth row and the ith column and then multiplying it by the ith element of the vector x. And that will, sometimes we'll use the feature vector f for the class y. And we'll compute fc for all the classes, c of 1 to capital C, for the number of total classes that we have. So if we have 5 classes, we compute f1, f2, f3, f4, and f5. All right, now a little bit more of notation. Basically here, in our case, the loss that we optimize for will maximize the probabilities of the correct class y. And so intuitively, we often minimize the negative log probability of that class. All right, some background. I don't think this will be very relevant for most of the class, but if you're familiar with information theory, it's definitely interesting to think of and keep these in mind sometimes. Basically, assuming that our ground truth, our goal or target probability distribution is usually 0, 1 vector or one hot vector, where all the probabilities for the classes that are not true are 0, and then we have probability of 1 for the class that we actually want to predict. If we assume that, and then we compute with the softmax our basically probability from the model that our softmax gives us, give an input vector, apply the softmax, get a probability out. So usually we call that Q. Now, basically, the cross entropy here for P and Q is defined with this, the negative of the sum of the probability of each class times the log of the probability that we predict for that class. And now, since we define P to be this one hot vector, we basically see that this is either 0 or it's 1. And so basically, we can only care about the log of the probability that we actually try to predict here. And we can also rewrite the cross entropy in terms of the entropy and the KL or Kullback-Leibler divergence. And again, it's not relevant if this is a little too fast, don't worry. Just want to make sure those of you familiar with information theory understand the difference. And it is actually, it's nice to know this here. It's very intuitive. Basically, the KL divergence is just this non-symmetric measure of the difference between these two probability distributions, P and Q. And because we can rewrite the cross entropy, this cross entropy error is actually the one we always optimize for when we train our softmax classifiers. So it's pretty important. When we rewrite it like this, you can see here that it basically is the sum, and we can look into that a little bit more also. Essentially, the entropy here of P is again 0 in our case, because again it's either 0 and 1, and it's also just a negative sum over the probability of each class times the log of that probability, and so that will be either you have the probability, which is 0, or the log that is 0. So h of P goes away. Also, P is of course the ground truth, so as we optimize anything, there's nothing to optimize there. So really, when we say we minimize, and this is the main takeaway message here, if we minimize the cross entropy between our target distribution and the distribution that our model gives, it's essentially minimizing the KL divergence between these two distributions. And again, sometimes people mistakenly say that KL divergence is a distance. It's not a true distance because it's actually a non-symmetric measure. All right. Again, it's just background. Don't worry if that was a little too fast. All right. In problem set 1, you'll derive the gradients of the cross entropy error with respect to all these different input word vectors that we have and the matrix W of the softmax. And that will familiarize yourself with the concepts to exactly the kind of degree that you need for the class. All right. And now it's 4:20. I think that's a good place to stop. Thank you.